due to the technical issues. Please bear with us.
Recording in progress.
Sir, we have a power issues here. Please hold for some few minutes, sir.
Check.
Sorry for that, and followed by some technical issue. First of all, I would like to thank Dr. M. Roja Raman for giving me this opportunity to talk about Lidar Technique for aerosol cloud interaction studies. In this presentation, I will be mainly emphasizing on to the application of Lidar Technique, especially for the aerosol cloud interaction studies. Next slide. So the outline of my talk is, so before understanding how the LIDAR can be used as a tool for aerosol cloud interaction studies, so it is important to have a look into the fundamentals of aerosol cloud interaction. I will be giving a brief account of aerosol cloud interaction. Next slide. So the aerosol cloud interaction is basically a cloud microphysical process which occurs particularly when you additional amount of aerosols are introduced into the cloud. So let me tell you how cloud forms. There are different ways for the cloud formation. A simplest way is by means of a convection. So we know the Earth receives radiation from the sun. As a surface heats up, the atmospheric air layer in contact with the surface gets heated up, and when this air parcel gets heated up, it becomes lesser dense, and then it goes up. So this ascent is basically governed by adiabatically. It takes place as the air parcel goes up adiabatically in order to adjust with the pressure differences. So it expands. So when the air parcel expands, it cools down. So as per the law of Clapeyron's equation, so when there is a decrease in as the temperature decreases, saturation vapor pressure also decreases, and the available water vapor in the air parcel becomes supersaturated. When the water vapor in the air parcel becomes supersaturated, it will try to find out some surface to condense, because it is a saturated air. Water vapor is saturated there. And in general, in the atmosphere, these surfaces or the particles, they're also known as aerosol particles. And this supersaturated water vapor condenses onto the aerosol particle, leading to the formation of a cloud. And these aerosol particles is a big set of particles. In that subset of particles are only having affinity to the water vapor. They are called the cloud condensation nuclei. It basically depends upon the aerosol chemical composition, size, and available supersaturation to actually make a cloud. The next slide. Yeah. No. One before. No, one before, please. Yes. Next. Yeah. No. So I told you the aerosol cloud interaction process basically takes place when additional amount of aerosols are entering into the cloud system. So there are different ways this is going to modify the properties of the cloud. So for example, this is a fresh cloud with this many number of cloud droplets got introduced to air pollution or more number of aerosols. What happens is this additional number of aerosols after entering into the cloud, so they try to compete with the water vapor to get the water vapor. So once they compete, because if the water vapor present in the cloud is limited, means so there is no exchange of water vapor between the cloud and the environment, it's a fixed. Then what I meant is this remaining water vapor try to condense on all the additional aerosol coming into the cloud. As part of this, it will lead to the formation of cloud droplet. But because more number of aerosols are there, less water vapor is present in the cloud, it will result into a small droplets, but more in number. So this is how it changes the cloud properties. This is called the first indirect effect or Tommy effect, because it was discovered by the same Tommy. That's why it's called as a Tommy effect. So once the more number of particles are there in a cloud, the cloud acts as a bigger surface area for reflection, and the same cloud now will reflect more radiation back to the space before to the as compared to the clean cloud. And that is why this is also called as a cloud albedo effect. And then subsequent to this, So what happens is, because we have more number of small droplets in the cloud, there is a process called the collision and coalescence process. That means cloud droplets come in contact with each other to grow in bigger size, bigger in such a way that they will come under the gravity. So, and then the precipitation starts. That is, the rain starts from the cloud. Because we have more number of small droplets, the collision and coalescence process will be delayed. I mean, it will take more time to grow into a much bigger droplet so that precipitation can occur. So, because of more lifetime, this cloud can stay there in the atmosphere for more lifetime, reflecting more radiation back to the space. So this is called the cloud lifetime effect, because of this, the lifetime of the cloud is increasing. Are also called the Elbeck, who has first observed this effect in the name of Elbeck. It is also called the Elbeck effect. So after this, the cloud starts seeing a different, cloud organization will start. Once the cloud is there for a long time, so this can take into different forms. So either the same cloud can develop vertically or horizontally. It all depends on the background dynamics. Next. So here I am showing some examples. If you take a non-precipitating cumulus cloud over a land, so this is normal cloud. And when it got introduced to the more pollution, so what actually happens is, so more number of small droplets will be formed in the cloud. So because these small droplets are formed, cloud lifetime will increase, as I told you before. But during this process, more lifetime, what happens is these small droplets in the cloud, they get dried up. So the water vapor around the droplets will evaporate, small droplets will evaporate, particularly at the top side of the cloud. Here the cooling will, radiative cooling will take place, and it will lead to the entrainment of dry air into the cloud. So because ultimately the cloud cloud size will decrease. Apart from this, we can also see, particularly over oceans. So when there is a clouds are there, they actually precipitate. When the clouds will precipitate, the cloud fraction will decrease. So leading to the open cells, different broken clouds will be seen over the oceans. But because of the introduction of this pollution, what happens is the cloud fraction increases and the broken clouds will come close together to form a big cloud. This usually can be seen in a marine stratocumulus clouds. And this is called the transformation of open to closed cell. And then if you see, these are all some of the processes, organization of clouds. Once the cloud aerosol interaction ignites into a cloud, organization of cloud take place. I have given example for cumulus clouds over the land and marine stratocumulus clouds over the ocean. When it comes to the convective cloud, this is a very interesting and special thing. So we see this is a convective system with a lot of cloud droplets in the below 0 degrees height and ice crystals over that height. So when this pristine convective cloud system got introduced to the more air pollution, what happens is more number of small droplets will be formed. So because of the abrupts within the cloud system, these more number of small droplets or aerosol particles will be taken up and up, just they will cross the 0 degree isotherm. As they cross the 0 degree isotherm, they will act as a ice nuclei for the formation of ice crystals. So once the ice crystals are formed, they will release a lot of latent heat because formation of water vapor to the droplet to the ice crystal will release more latent heat. When this more latent heat is released, so that makes the air parcel to go up because of the latent heat release. And this same cloud now will grow into taller and taller clouds and with larger annual clouds. Because this process is, because of this process, cloud lifetime is delayed again in the convective systems. These annual clouds grow into bigger and larger, so that they will act as a they will stop the outgoing long wave radiation. At the same time, they will reflect the incoming short wave radiation. So these are the this effect is called the thermodynamic invigoration. So cloud is invigorated, is growing bigger because of this process. This is called the cloud invigoration. In particular, this is called the thermodynamic invigoration. There are again two more mechanisms explaining the particularly the cloud invigoration in deep convective clouds. So they are called microphysical invigoration and humidity invigoration. I am not going into the details. The next slide. So I have talked about the basic fundamental process of aerosol cloud interaction. So how the interaction takes place and all. Now, if you want to see whether the interaction has taken place in a cloud, you need to measure it, quantify it, or estimate it. So, Fieldgold et al., they have proposed mathematical formulations purely based on the physical laws governed by both aerosol and clouds. As per the formulations, so these aerosol cloud interactions can be estimated in 3 ways. So one is, so you look into the cloud droplet radius or effective radius, and then cloud optical depth, and then cloud number concentration. So these 3 parameters from the from as far as the cloud point of view. From the aerosol point of view, one can have either aerosol extinction coefficient or backscatter coefficient or aerosol optical depth from aerosol point of view. And the partial derivative of the cloud optical depth as a function of aerosol property gives the estimate of the aerosol cloud interaction. Similarly, partial derivative of effective radius as a function of aerosol optical depth gives the gives the aerosol cloud interaction estimate. And then finally, for these 2 cases, the values usually are seen between 0 and 0.33. And the last case is the cloud number concentration. We are seeing changes in the number concentration. This is not a partial derivative. So the other 2 are partial derivatives, because for the other 2 to take place, the water content in the cloud should be limited. Okay. So that's why they are partial derivatives. The last one is not a partial derivative. The number of particles increasing as a function of aerosol. The derivative is called the aerosol, is the estimate of aerosol cloud interaction there. And these 2 basically equations will look into the changes in droplet size of the cloud. This particular equation will look into the changes in droplet number concentration of the cloud. Okay, these are the basic mathematical equations used in used by many researchers in the estimation of aerosol clouds interaction, especially in the liquid clouds. So next slide. So coming to the Lidar. So Lidar, how the Lidar can be used in this context, aerosol cloud interaction, understanding the aerosol cloud interaction. So the approach is like this. So one can have a Lidar which can provide the aerosol information and also the aerosol cloud-based information. And then one can also have the microwave radiometer which can provide the cloud water content. And one can have the microwave cloud radar, which can provide, in combination with microwave radiometer, so which can provide the cloud droplet effective radius and the cloud droplet number concentration. So as shown in this table, this is the combination of these instrumental setup can be used exclusively for understanding aerosol cloud interactions. All the setup can be operated round the clock and to have a better observation of aerosol cloud interactions. So coming here, the Lidar is the important thing here, because Lidar only gives, in this setup, Lidar provides the aerosol information. So in particular, I am showing here, this is called the celometer, the Lidar. In place of celometer, one can have a micropulse Lidar also, or one can have a Raman Lidar also. But better to have a Lidar which can operate both during day and night time, so that we can have a continuous observation, round the clock observations. Next slide. So using this similar kind of setups, so there have been many studies. I will give you some glimpses from those very important studies. So first, the classic paper by Fieldgold et al. Published in 2003. So first, they were the first people to show the observational evidence of aerosol cloud interaction in the low clouds. So what they have shown here is the aerosol extinction coefficient, aerosol and then cloud effective radius as a function of aerosol extinction coefficient. So these logarithm of aerosol extinction coefficient and logarithm of particle radius. This shows a negative slope, and the index they calculated is for different liquid water contents. So they have limited the water content in a cloud, and the 100 to 110 grams, 110 to 120, and 120 to 130 grams. And this is one case of observation took place on April 3rd. In the next later case of observation on 21st October also, they found a similar kind of negative slope between the same parameters for different liquid water contents. But here it is one thing we need to observe here is that the estimated indirect effect decreases with the increase in the water content. This is because, so more the water content, in the liquid cloud, the effect of aerosol cloud interaction process will be minimized because there comes into picture other dominant processes like maybe collision coalition process, etc. So the effect will be minimized, and this shows that we can see the aerosol cloud interaction process basically in the cloud only when the liquid water content in the cloud is not very much. Okay, and then next slide. Yeah, so to study the aerosol cloud interaction, it is very important to segregate the data very carefully, because we are using a different kind of instruments, and we are operating the instruments around the clock. What we have to do, we have to make sure that we are collecting the right data set. So this is again an example from a case study from Gross USA Island, Azores, published by Sarna and Rosenberg. So what they have done is they have operated a microwave radiometer, ceilometer, and a cloud radar. For the one case, what they before collecting the data to see the aerosol cloud interaction, so they have taken care exclusively. So they have taken only those clouds which are in the boundary layer, just below the boundary layer, just above the boundary layer. So and then assume that throughout the boundary layer, aerosol concentration or aerosol pollution is uniformly distributed. And so with these assumptions, and they have taken the aerosol data from 300 meters below the cloud base. And so with these all careful considerations, what they have seen is that the slope between this is a scatter plot basically, the scatter between the cloud aerosol property and the cloud property, effective radius in this case. So for different liquid water contents. So again, when you are looking into the aerosol property and cloud property, cloud radiative effective radius, you have to see in different liquid water contents, and they found that the correlation, if you see the effective radius, the correlation is decreasing as the water content is increasing. And similarly, so in this case, instead of effective radius, they have shown the droplet number concentration. So as a function of droplet number concentration, there is a positive relation between the aerosol property and cloud property. Next. So, because cloud is a system, it is not lying in an ideal system. It is lying in an atmospheric system. So it is subject to the environment surrounding the atmosphere. So in this scenario, what are the changes taking place in the cloud? It needs to be carefully looked whether those changes are because of aerosol or because of other parameters. That is very important. So one of the other parameters are dynamical parameters which can affect the cloud properties is the updrafts in the cloud. So here what they have shown is when they have categorized the cases where there is only updraft in the below the cloud base, they found a strong correlation, negative correlation between the strong negative correlation between the cloud properties and aerosol properties, and strong positive correlation between the aerosol properties and cloud number concentration. So for the cases of updraft categories shown in the diamond symbol, so aerosol cloud interaction index is high, higher than the water circles, which is for all the cases. And then next slide. So similarly, Schmidt et al. 2015, they have also used a Lidar system for the aerosol cloud interaction studies. But this study is a peculiar, a novel study, because in this study they have used only Lidars, all Lidars. They have used a dual field of view Raman Lidar for getting both aerosol and cloud properties, aerosol extinction, cloud number concentration, and then cloud effective radius. And aerosol extinction, and then they have used a Doppler lidar for getting the wind information. So whether there is any updraft or downdraft. So using this a unique novel approach, what they have found is this is the aerosol cloud interaction index estimated for two different liquid water content cases, and we can see that there is a change in the index estimated between the aerosol particle extinction and the effective radius and both the number concentration. So here the negative relation, here the positive relation. And during the updrafts, they have seen the aerosol cloud interaction index is more because of the updrafts taking more aerosol into the cloud, leading to the aerosol cloud interaction process. Next slide. So this is how lidars come into picture when as far as aerosol cloud interaction studies are concerned. And of course, they are very important because they provide valuable information of aerosol cloud interaction. But what happens is lidars, they look at zenith. So they provide only the backscattered information. And whatever you are looking is not sure whether you are looking at the same cloud, at the evolution of the cloud, starting from its pristine condition to the polluted condition, or it is a passing cloud. So that uncertainty is there when using the lidars. And then top-down looking lidars, they are not able to measure the aerosols, particularly below the cloud base. Because the pollution is coming from cloud base, the top-down looking lidars are unable to measure the pollution below the cloud base, and it's not going to be useful. And then bottom-up looking lidars, they cannot completely penetrate through the cloud, even liquid clouds also. Forget about the convective clouds, even liquid clouds also. Sometimes if the thick clouds are there, there is a high chance that lidars will be attenuated. And then because of these things, top side, whatever is happening in the top side of the cloud, it will be completely blind to us. So these are all some of the limitations of LiDAR when you are using, especially for the aerosol cloud interaction studies. Next slide. So, there is one other way which we thought of to overcome this type of situations. That is using along with the lidars, using a balloon bone in situ measurements. So this is what we call it as a balloon bone aerosol cloud interaction studies, a field campaign. With this thought, we started a field campaign named BASIS Balloon Bone Aerosol Cloud Interaction Studies. So wherein which we are operating all the three important instruments like radar, LiDAR, and then and along with radars and LiDARs, microwave radiometer, and then a balloon along with this a balloon. So we used very peculiar, specialized sondes for this purpose. This is called the cobalt sonde. So yesterday in an inaugural talk, Dr. Jean Paul told about this cobalt sonde. So he has compared the Calypso data with this cobalt balloon bone measurements. And now, and apart from, along with this, we are using the, another thing is the CPS sonde. This is called the cloud particle sensor sonde. So this combination, what it gives is, so this cobalt gives both aerosol and cloud in a profile. And then cobalt, CPS gives only cloud. So aerosol and cloud. So we can simply separate the aerosol and cloud in a profile. This was the idea. And then apart from this, these balloons, they are able to pass through the cloud. So from below to above cloud, which LiDARs are not able to. So with that, even though there is a even though balloon drifts away from the launch site for about 10 to 12 kilometers, that there is a good chance that at the lower heights, balloon may not drift that much, and this everything will be in the same field of view. So both all the instruments like LiDARs, ground-based instruments, and satellite instruments, and it will be in the same field of view, so that we'll get a good information, which by using a in situ balloon bone in situ measurements, which probably missed by a LiDAR. So with this motive, we conducted 15 field campaigns from Gadanki. Next slide. So I'm showing here because we operated everything. So I'm showing here how these LiDAR observations are compared to the balloon measurements. What is that is missed in the LiDAR observations. And then if you see, this is a profile of cobalt backscatter ratio, and this is the particle number concentration from CPS, and this is the range corrected signal. We have restricted ourselves at range corrected signal only, because when you derive the properties like aerosol extinction or cloud properties, we will be employing many algorithms, retrieval algorithms, which they themselves have a lot of uncertainty and which simply can propagate into the final product. So in fact, we want to just quantitatively compare how the ground-based LiDAR observation, balloon observations look into. So that we restricted to range-corrected signal from all the three LiDARs as shown here, space-bound Calypso LiDAR, micropulse LiDAR, and my LiDAR. And we can see wherever wherever the balloon has detected a cloud, the same altitude LiDARs are also detecting the cloud layers. But apart from that, the top portion of the cloud layers are which are missed by the LiDARs, ground-based LiDARs are seen in the balloon. At the same time, the bottom portion of the cloud layers, which are missed by the space-bound LiDARs, are seen by the balloon. So in this way, the balloon measurements are providing the information, which in a way it is additional information to the existing information. Next slide. So then finally, we using this balloon information, what we have done is we attempted to estimate the aerosol cloud interactions. We had about 6 liquid cloud observations from the basis campaigns, and we have plotted. So we have plotted aerosol information that is coming from the balloon, that cobalt backscatter, logarithm value of cobalt backscatter and then logarithm value of cloud particle number concentration from the CPS sound test. And now we found that the slope values is about so the slope values is about 0.7. So it should be between 0 and 1. And this estimate, the slope estimate, has been carried out for 3 categories. That is from cloud base to 300, 400, and 500 meters separately. And we have taken care of the water content relative humidity below the cloud using the removal methods. We have removed the influence of the possible influence of the humidity onto the aerosols, and then we have taken only removed aerosol content below the cloud, and then we got a good positive correlation between the cloud droplet number concentration and aerosol. So like this aerosol, next slide. So finally, I would like to summarize this way. So as per the latest IPCC report, AR6, even if AR6, you see effective radiative forcing from the aerosol cloud interaction. That is the changes in the modification of the aerosol properties and the organization of the clouds in response to the aerosol cloud interaction. Altogether, what is the effect of radiative effect that you see, that is called the effective radiative forcing. Is observation based on observations, it is -1 plus or minus 0.7 watt per meter square. The uncertainty is really very high. Still, as of now, the uncertainty is very high. So it is very important to understand the aerosol cloud interactions in and about. Either it can be through observations or modeling studies. And then when it comes to the Lidar, is definitely a useful tool for aerosol cloud interaction studies, as they provide the best possible information about the aerosols and about the cloud base. However, due to penetration losses, Lidar lacks in complete aerosol profiling. And then with additional capabilities such as if you use LiDARs with the dual polarization capability, daytime and nighttime operation capability. So undoubtedly will be a powerful tool for aerosol cloud interaction studies, as we have already seen.